Okay, class, let us see the kinetics of polymerization. Introduction. Having dealt with various polymerization reactions in chapter 2, the present chapter covers kinetic aspects of some of those reactions. Kinetics has a bearing on the speed of a reaction. So what is kinetic? Speed of the reaction under a given set of conditions, and on how this condition will influence, among other things, the polymer molecular weight distribution, chemical composition, and indeed the extent of polymer conversion. Let us look into some of these aspects. Free radical chain polymerization. So we all know free radical chain polymerization comprises of three steps: initiation, propagation, and termination. To initiate the reaction, there must be free radicals available, which are usually generated by homolytic decomposition of an initiator. So this is the initiator, this is the rate constant of decomposition, initiator decomposition rate constant, okay, and these are the free radical generation. So here I is the initiator, R star is the free radical form, KD is the initiator decomposition rate constant. The rate of decomposition RD, capital RD, is related to the concentration of the initiator by the following equation. So RD equals to 2 times KDI. Why 2? Because 2 free radicals are formed. And also negative ddt of I, because in the reactant side it is being consumed, so its concentration is decreasing. So the factor 2, and this is in the product side, so therefore this is positive. The factor 2 is used in equation 4.2 as a pair of radicals produced by decomposing one molecule of the initiator. From Arrhenius equation, we know that the rate constant is related to temperature as follows. Arrhenius equation is rate constant is equals to A, capital A, e raised to the power minus E by RT. A is the constant called the frequency factor. A is the activation energy term. R is the gas constant. P is the temperature in the absolute scale. Substituting KD from equation 4.3 into equation 4.2. So I'll pick this up and put it here. Okay. So I will get 2A e raised to the power RT I. E raised to E upon RT into concentration of initiator. This equation tells us that the rate of decomposition of an initiator R, capital RD, increases with temperature and concentration of the initiator. The free radicals generated by the decomposition of initiator are shown in the equation 4.1. As shown in the equation 4.1, can attack monomer to give a new free radical as shown. So this is the initiation step where the first fresh monomeric species is getting attacked by the free radical, and we are getting a new free radical, where M is the monomer, AI is the initiator rate constant. The rate of initiation is denoted by capital Ri and may be written as Ri equals to Ki Rm R star M, and this is being consumed, this monomer, therefore negative ddt of M. The free radicals have such a high reactivity. These free radicals have very high reactivity that as soon as they are formed by the decomposition of initiator, they attack the monomer and start the initiation process. So we can assume therefore that the rate of formation of free radicals equals to the rate of disappearance of the same, according to equation 4.5. This is equation 4.5. So we can therefore visualize Ri is equals to Rd. So rate of initiation is equals to rate of decomposition. Therefore Ri can now be written as 2 times Kdi. This one. This Rd is equals to Ri. Therefore Ri equals to 2 times Kdi. This equation holds good when all the free radicals produced are effective in the initiating the chain, polymer chain growth. In actual practice, some of them are not effective. 100% efficiency is never there. since they are lost as side products by way of process such as recombination. If we denote the F, the fraction of free radicals produced, that is effective in initiating the chain growth, then Ri can be further modified as Ri equals to 2 times F kdi. This F is the fraction of the free radical produced that is effective in initiating the chain growth. This value of F is between 0.6 to 1. Okay. This gives us the efficiency of the initiator. The value of 0.6 indicates that only 60% of the free radical generated have effectively initiated chain growth, the remaining 40% being lost as side products. Now initiation is followed by propagation step, which is represented as follows. Propagation, fresh pneumonic species getting added to the initiated chain and then chain is being propagated, where Kp is the propagation rate constant. The rate of propagation is represented by. So this propagation rate constant is different and rate of propagation is different. Okay, rate of propagation is represented by capital RP and propagation rate constant is noted by small k and in suffix this small p. So now this rate of propagation is equals to propagation rate constant into m star to m, and m is being consumed, therefore minus ddt of m. From equation 4.10 we understand that the propagation rate is proportional to m star concentration, the concentration of the reactive free radical site, that is the concentration of the going chain, as well as m, the concentration of the mono. So using this is proportional to these two. The final step in polymerization is termination. If termination occurs by the combination of growing chain, that is coupling, it can be represented as follows: R M N1 M star R M N2 M star, and they couple to give. This is the termination rate constant, and R N2 M M and R M N1 M M M N2 R. So this is termination by coupling. Okay. Both of these free radical sites have formed a sigma bond. Yeah. The corresponding rate equation for termination process is given by, since M is being consumed, so minus ddt of M star and RT, rate of termination, 2 times KT M star square. Okay. However, when the steady state prevails, that is when the number of chain growth initiated equals the number of chain growth arrested, the rate of initiation is equals to the rate of termination. So suppose there is a steady state, means ideal state, when the number of chain growth initiated is equal to the number of chain growth arrested, then Ri will be equal to Rt. Therefore, from equation 4.12 and 4.8, this is 4.12 and this is 4.8. So equating them, we get 2 Fi equals to 2 M star square. So M star square, taking it on the left hand side, all the terms, other terms on the right hand side, we get this. Now the square side goes to this RHS, it turns into to the power half. From equation 4.10, we know the value, we get the value of M star as 4.10. M star as this rate of propagation in upon kpm. This, on substituting this in 4.14, this one, we get this equation. Now, taking this rate of propagation of LHS left hand side and everything on the right hand side, we get this Kp to Kd raised to the power half, Kt raised to the power half, Fi raised to the power half, and into M. The equation 4.16 is what we get. This equation states that the rate of polymer formation is proportional to the first power of the monomer concentration and also to the square root of the initiator concentration. I hope you understand only this much that you have to know about the kinetics of polymerization. Okay, it is quite tricky, but if you read it again and again, you'll get